Okay. Well, let's go and get going for today. So, one announcement. Actually, there's two announcements. First one, we're changing the recitation rooms the review rooms. The rooms for the review that are meeting on Friday in the morning and in the afternoon. So we're going to move those to AZ E210. Okay, E is important because there's also a W210. So go to E210 and you'll find your review. The one that meets on Sunday, run by Ben, that'll remain in the MRB building because we don't have access to that AZ building over the weekend, okay? So the second announcement is that Quiz 8 is due tonight. We should cover the material for Quiz 8 today. I will make an announcement in the class if I don't get through everything that I think I'm going to get through. Okay, but I think I will. So I think we'll be fine with that. Okay? All right. Our riddle, there was a man one night. He started to run straight forward. Then he turned left. Soon after, he turned left again. Then he started running toward home. When he got home, there were two masked men waiting for him. Who were they? The catcher and the umpire. That's right. This is a very good riddle for today because tomorrow is opening day for Major League Baseball. Right there. Okay, so there's so many good things that happen in the spring. I mean, baseball starts and the weather gets nice and baseball starts and the trees start to bud and baseball starts and flowers start to bloom and baseball starts, right? See, there's this correlation with life coming back to the world as baseball starts. But anyway, that won't be on the next exam. But anyway, okay, so we have a little bit of work left to do in Lecture 7 that we left off on the day before spring break. So I want to return to that. Only one slide that I'm going to go through, and then we'll jump into chapter or Lecture 8, and we'll review the citric acid cycle, which of course on Monday you and your partners went through the citric acid cycle and also the amount of ATP that can be produced through the complete oxidation of glucose. So what we have, though, left in terms of Lecture 7, remember Lecture 7, we looked at the entire five-step process required to convert or oxidatively decarboxylate pyruvate into acetyl-CoA. And it was that large enzyme complex, pyruvate dehydrogenase complex, that did that. And it had three enzymes really, E1, E2, and E3. Right? That enzyme catalyzes an irreversible step in the cell. It is a regulated step. In fact, it's tightly regulated. And so I wanted to talk about its regulation, and then we'll move into Lecture 8. First of all, the complex itself can be competitively inhibited by its two products. Okay, so acetyl-CoA and NADH, both of these will feed back and competitively inhibit the enzyme. So acetyl-CoA will inhibit E2 competitively. This is where it's produced. It will, at high enough levels, remain in the active site, preventing further catalysis. NADH gets produced by E3, and this will competitively inhibit the active site of E3. Okay? So that's one aspect of the regulation of pyruvate dehydrogenase complex. Now, below that, so if we were to cut this in half, below that line, you'll see covalent modification of the complex, specifically at E1. So pyruvate dehydrogenase is the subunit that we called E1 on the Friday before break. And it can undergo covalent modification, specifically phosphorylation, as you see here. And that phosphorylation will inactivate the enzyme. Okay. Now this is true in mammalian systems. Not true for all organisms, but certainly true in mammalian systems. Okay. There is a kinase. It is just listed here as kinase. Really, this would be better referred to as PDC kinase, or maybe even PDH kinase. Okay. And that kinase will be activated by both NADH and acetyl-CoA, the products of PDC. If that's activating, Okay, so this is activating an effect on that. If it's activating the kinase is then phosphorylating E1 and inhibiting E1. So in totality, the signal of NADH and acetyl-CoA or acetyl-CoA are to inhibit the complex. Okay. And one of the key aspects of that, specifically for mammalian cells, is that once pyruvate is converted to acetyl-CoA, we can't recover those carbons to become a sugar, a glucose. Okay, so one aspect of this that's important to prevent that process, okay, if you have enough acetyl-CoA, there's no reason to continue to move that to move pyruvate into acetyl-CoA, simply because you lose the capacity to then make glucose from that. Okay. Now, coming back to the lower half of this, we could go on and on about all these different signals, but let me go ahead and highlight two more here. Okay. Increasing levels of NAD plus and ADP will inactivate this. Okay. And if they're inactivating the kinase, then they're preventing phosphorylation, which means that the enzyme will be more likely to be active, okay, preventing the inactivation of it. Okay. Furthermore, on the other side of this, there would be this phosphatase. Again, we could call it PDC or even PDH phosphatase. Okay. And that is activated, you'll see here, by magnesium and calcium. Talk too much about the different reasons why calcium or magnesium will rise in the cell, but they can do so for a variety of reasons. Calcium is an important secondary messenger of many signaling pathways. Okay, so it's also released in muscle contraction as well. In that case, probably the most obvious reason why you'd see the activation of the phosphatase, because the activation of the phosphatase removes the phosphate, activates PDH. Okay, activating the complex as a whole, you'll get more flux through then energy-producing pathways when calcium is higher, and that will be higher in cells that are active, like muscle cells that are actively contracting. Okay, so there are other reasons, certainly. That's one scenario, but there are other reasons. Okay. And that's all I want to say in terms of regulation of PDC. Okay. Can undergo phosphorylation, dephosphorylation, as well as the competitive inhibition. Okay. Questions on that? Okay, let's go ahead and do this then. Let's move forward now to not that, because that's a different class altogether. Okay, there we go. Let's move forward now and start talking about the citric acid cycle. Okay, so I want to quickly review the pathway as a whole. Of course, you went over it yesterday. This is a really, well-known central metabolic pathway. I'm certain that you've heard about it in other classes. You've probably gone over it in other classes. We have to, of course, in a metabolism class, go over it. It can be considered, in some senses, the hub of metabolism. All right, so we're going to review that. I don't want to spend a ton of time on that. Move to regulation, and then we'll probably today end with this term amphibolic, okay, and we'll define that and what that means and the importance of that. But let's go ahead and think about the pathway, and I'm going to put it in its context in terms of catabolism, just to give you, again, try and give you that bigger picture. That's what I want to go for in this class, is that you guys would have a large metabolic map in your mind at the end of all of this. Okay, so let's do this. We have been talking up to this point about the oxidation, of a 6-carbon sugar. Glucose, of course, is what we spend our time thinking about. This is the reaction. I've never actually, I don't think, written it down this way in this class, but I'm going to go ahead and do so now. Okay, but if you were to carry out in totality cellular respiration, this is the reaction that you get. Okay, I think I did do this on the very first day. We talked about gummy bears. and it blew up, right? This is our reaction, okay, as a whole. I said that the major difference between what went on in that beaker and what goes on in our bodies is there are lots of little steps, okay? So we've gone through quite a bit of those steps, actually. We've seen now how this molecule can become, of course, 2 pyruvates, okay? Small amount of NADH is made in that process. Small amount of ATP is made in that process. Okay, we just went through in lecture 7 how that can be oxidatively decarboxylated to make 2 acetyl-CoAs. Okay, decarboxylation leads to here 2 CO2s. Okay, you'll notice in our reaction above there's a total of 6 moles of CO2 that will be produced for every mole of glucose that is going to be oxidized. 2 of them have now been produced, okay? And electrons are being sucked off of these molecules, okay, put on NADH. Right now, what we did, or what you all did on Monday in your group work, is that you looked at the citric acid cycle. The citric acid cycle starts with a C4, oxaloacetate, condenses these as a condensation reaction, acetyl-CoA and that oxaloacetate, and it makes citrate, okay, 6-carbon molecule. And then that 6-carbon molecule will undergo decarboxylation to a 5-carbon molecule, alpha-ketoglutarate, okay. This will make more NADH. Oops. This will make more carbon dioxide. Okay. And I guess I should be keeping my stoichiometry consistent here. 2, 2, 2. Okay. So more carbon dioxide is made here. Right? Now, keep going on here. This is going to go through another oxidative decarboxylation, become a C4. More NADH is made in this process. More CO2. Okay? Now at this point in time, highlight for you, we're about halfway through the citric acid cycle, and if you notice that the carbon dioxides that have been produced now total 6. Okay? And quite a bit of electrons have been removed from those carbons that were originally derived from glucose. Okay? Now, we'll do this one more step here. That C4 will be converted to a different C4. Okay, the C4 here at the bottom of the circle will be succinyl-CoA. Okay, in that process, again, a small amount of ATP or GTP. I'll go ahead and put GTP, but we could say ATP as well. It depends on the isoform of this enzyme. Small amount of GTP will be made. A small amount of FADH2 will be made, and a small amount of NADH will be made. Okay? And that will be essentially the oxidation of the carbons in glucose once that entire process is complete. Now, we have yet to look at the process that's going to make water from oxygen, but we're going to do that in our next set of lecture notes. We will see how oxygen becomes water. And to do that, all this NADH and FADH2 that's been produced in these processes are going to feed their electrons into an electron transport chain. Okay? And that electron transport chain is going to pass electrons through these multi-subunit enzyme complexes to oxygen making water. Store energy in a proton gradient, make ATP, a lot of ATP. Okay? And we'll get to that that table essentially that you guys all filled out yesterday or Monday, the second portion of the group work, where the complete oxidation of glucose will make about 32 ATP. We'll talk about where those numbers come from when we get to lecture 9. Okay. Why did I say that an NADH equals 2.5 ATP or FADH2 equals 1.5 ATP? We'll talk about that. I'll show you that. Okay. And those numbers can vary. And we'll talk about reasons why that's the case as well. Okay. So that's the big picture, right? I would hope that you could remember this even a couple years down the road. I doubt that unless you're working on the citric acid cycle every day that you're going to remember the names of all of the enzymes and substrates. You might, and good on you, right? But you probably won't. Shame on you. Okay. Okay. Hey now, right? All right. Questions? Big picture. A little bit more detailed picture here, right? So this is hopefully something that you looked at as you went through your group work on Monday. So let me do this. I want to go ahead and start essentially right here, oxaloacetate. And I want to start by asking you all a question. So let's do this, because there's some nuances to this pathway that you wouldn't necessarily get in a group work discussion on this. Okay, so let me expand this here. I'll give you about 2 minutes to answer this question. But the standard free energy change of MDH, and you say, what's MDH? MDH is malate dehydrogenase. It catalyzes the last step in glycolysis. Okay, so it converts malate to oxaloacetate and makes NADH. So that standard free energy change is 29 kilojoules per mole, whereas the actual free energy change is about 0. Okay, cellular conditions are reversible. Given this and the fact that NAD-NADH ratio is about 10, what would you expect the relative concentration of OAA to be? Relative, low or high? What do you think? Is OAA going to be low or high based off of this data? And how in the world would you know that? So I'll give you 2 minutes to respond. All I need is a text saying low or high. On your marks, get set, go. What do you think? Okay. You could talk to your neighbor about that too, and the nice weather and the fact that the Rockies start tomorrow. Okay. Hopefully biochemistry though. About 20 seconds left, so submit an answer if you haven't done so. Okay. Okay. Let's check this out. So we'll jump right to a word cloud. Biggest word here will, okay. Low, high. Who high? I don't know what those other ones mean, and 5 is an interesting one, right? I don't know. 5. It's the right answer, 5. Actually, I was looking for the answer as 5. Good job. Whoever did that, good job. I wonder how many people put 5. I'm venturing to say 1. But anyway, low or high, it looks like there's almost an even split between low or highs. And some of you, honestly, when you look at this question, you're like, boy, there's a bunch of stuff up there that I don't even know where to start. How do you start on this question? So let's do that, okay? And let me take you this. This takes us to some of the nuance of this pathway for certain, but it also reminds us of some of the aspects of thermodynamics and how they are applicable to then metabolic pathways. So let's do this first of all, trying to find some blank space on this. Delta G, standard free energies, okay, is equal to negative RT natural log KEQ. Okay? R being universal gas constant, T being temperature. So the only thing that really standard free energy change is dependent upon is the equilibrium constant. Okay? So the equilibrium constant for our reaction that we're talking about, and the reaction that we're talking about, just so we have some sense of this, is this guy right here. Okay? That's the reaction we're talking about. That equilibrium concentration, or equilibrium constant, is going to be concentration of products, OAA and NADH, the way it's drawn for the citric acid cycle, over the reactants. Malate, I'll just abbreviate MAL, and then NAD plus is another reactant. Okay? Now, when we look at the delta G here, I gave you that value. I said, well, that's positive 29 kilojoules per mole. Okay? Well, if you do the arithmetic with this, you will find out that that then is going to lead to an equilibrium constant that's really small. It's going to be about 1.4 times 10 to the negative fifth. That's a small equilibrium constant, which means that this reaction at equilibrium will heavily favor reactants. Okay? However, I told you in the question that NADH, cellular NADH, NAD plus ratio is about 10 to 1. So this is going to be 10, and this is going to be 1. Now that has to then come to essentially 1.4 times 10 to the negative fifth, which means that this value here at equilibrium is going to be really, really low. Okay? So a very, very small amount of oxaloacetate. Now, I also said that, by the way, okay, in that question, delta G, actual free energy, is about 0, which means that the reaction is held at equilibrium in the cell. Which means that in a cell, in the mitochondria, there is very, very small concentration of oxaloacetate. It's in the micromolar quantities. Okay? Given the volume of the matrix of the mitochondria, we could number the number of oxaloacetate molecules in the hundreds, okay, or even below 100. That's a very small number of molecules. Okay, usually you think about thousands, tens to hundreds, if not millions, of the molecules in the cell. Okay, so this is a really low concentration. Now, why do I bring that up to start this whole discussion off? Well, the reason I bring it up is because oxaloacetate is the initial substrate of the reaction, of the pathway. That and acetyl-CoA. Okay, these combine to make citrate. Okay, and one of the irreversible steps, as hopefully you all recognized yesterday, was citrate synthase. That enzyme, okay, that's catalyzing this. So this enzyme is irreversible. Despite low concentrations of OAA. Right? Low concentrations of reactants tend to make reactions not exergonic, but rather inorganic. In this case, though, this exergonic, still irreversible. Okay? And the reason that that is the case is because there's a lot of energy stored right here. Okay? In acetyl-CoA, there's a thioester. Okay, and this stores energy. Now, the energy it stores is the energy it gets from the PDC reaction. I didn't talk about it on the Friday before break, but in E1, there's a redox reaction, right, that moves an acetyl group from E1 to the arm. That redox reaction is actually step number 2, if you go back and look at your notes. That redox reaction is really exergonic. The free energy, though, of that reaction is stored in a thioester, and that gets transferred to acetyl-CoA. So acetyl-CoA is one of these quote-unquote high-energy compounds. Right? That energy essentially kickstarts the citric acid cycle. A way to think about it is if you've ever mowed a lawn, you've pull the ripcord, right, on your lawnmower. That's kind of the idea here. It gets the whole thing running, right? So that thioester provides enough free energy to get this thing moving, despite the fact that oxoacetate concentrations are really quite low. Okay. Citrate synthase is an irreversible step because of that energy. And that's a nuance of the citric acid cycle. Okay. Certainly a nuance. Questions on that? Concerns? No? Okay. Okay, well, let's go ahead and move on then. We'll move down the list here. I'm not going to stop at every step in the pathway for sure, but let me go ahead and point out some things here. The next two enzymes that I want to highlight, these are also irreversible. So delta G's of these are less than 0. Very important regulatory steps: isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase complex. Okay, these produce CO2. Okay, so if you're referencing that last slide, that's where our CO2 production occurs. Both of them also produce some NADH, as illustrated on this slide. Okay. So 3 of the 8 steps, if you're counting, there are 8 total enzymes, 8 total steps then. 3 of them are irreversible. Citrate synthase, okay, isocitrate dehydrogenase, and then alpha-ketoglutarate dehydrogenase complex. We'll talk about the regulation of those in upcoming slides. You come down here, a couple more things to say. Let me go ahead and highlight this. You got another here, thioester. Thioesters are great ways to store energy. Okay? The thioester is part of this molecule succinyl-CoA. Succinyl-CoA is essentially the same thing as acetyl-CoA except for 2 more carbons. Okay? So it's made by, you'll notice this enzyme here, it's made by this enzyme alpha-ketoglutarate dehydrogenase, and you'll notice that term complex. That enzyme is virtually identical to the pyruvate dehydrogenase complex. It's comprised of E1, E2, and E3. It has this huge, complicated structural architecture, and it carries out 5 steps by these 3 different enzymes, okay? We're not going to go over the mechanism. We essentially did it on the Friday before break, okay? In fact, E3, the subunit E3 in this complex and pyruvate dehydrogenase complex is identical. They're the exact same enzyme. E1 and E2 have slight differences because the substrates are different, okay? But very, very similar reaction catalyzed there. It makes succinyl-CoA. Okay, now that energy, it says thioesters are stored in stored energy, right? That energy is used to make, it says GTP, or it puts in parentheses ATP. Succinyl-CoA synthetase, that's this enzyme that's going to use that energy from succinyl-CoA. That is going to, depending on the isoform, can make either GTP or ATP. Okay. Like I think, and I'm pretty sure this is the case, in the liver, the isoform makes GTP, which is interesting because the liver needs GTP to make glucose. Okay, so. Okay, now the last thing I want to go ahead and say here, and then we'll be done reviewing the pathway. Succinate dehydrogenase, you wouldn't have probably recognized this in your discussion with your group. This is also what we will commonly call in our next set of lecture notes complex 2. Okay? And there was, I do remember one group talking about this, okay? This FADH2 will actually transfer its electrons to something called QH2. Okay? And we'll look at that later on. Okay. I do want to just point this out, though, because the way we draw this, and I've never seen a book draw it any way but this, The way we draw FADH2, it gives this impression that FADH2 is released from the enzyme, diffuses somewhere, and then gives up its electrons. And that's not the case. So this FADH2 receives electrons from succinate and then passes them, because it's part of the electron transport chain, passes them on through the rest of the electron transport chain. Okay? FADH2 never actually leaves the enzyme. Okay? And that's typically true of FAD. Okay? They are usually permanently bound to the enzymes that they're found in. That's not true of NADH. NADH is a diffusible electron carrier. It will bind to an enzyme and then release the enzyme and diffuse through the cell. And that's, I mean, there's lots of details that we're kind of glazing over here, but that's, I think, a solid enough review based off of what you've done on Monday to get us through the rest of the class. Any questions of this? The citric acid cycle is so much fun that we should talk about its regulation. Let's talk about its regulation. Okay, let's do it. All right, so regulation, those 3 steps that we're going to look at. So the first step, again, just to give you some context here, citrate synthase. That's the one that we're looking at over here. This enzyme's regulation is interesting, to say the least. Let's put it this way. The enzyme's not saturated in the cell, okay, and it's also cooperative, which means that it's very sensitive to changes in substrate concentration. So let me illustrate what I mean by this. If you were to consider this graphically, this would be the rate excuse me, of citrate synthase versus substrate concentration. It's got sigmoidal behavior because it's cooperative, okay, but it's not saturated, meaning it's not at its Vmax. Okay, so we can think of it this way. Right? These are its 2 substrates, oxoacetate and acetyl-CoA. If we were to think about, let's say, here, let's just say that that's a steady state concentration of substrate. Put this over here. Okay? And you can see it would appear, based off of what I'm drawing here, to have some, velocity that's lower than 50%. Okay? If acetyl-CoA or oxoacetate concentrations start to rise in the cell, okay, it doesn't take very much, okay, elevation of those 2 substrates to have a fairly drastic effect on rate, right? So this is rising substrate concentration. And you can see this massive jump in velocity. That's really the main way that citrate synthase is regulated, just based off of substrate availability. If acetyl-CoA concentrations are going up, citrate synthase velocity is usually going up. Okay? And acetyl-CoA can go up for a variety of reasons, whether that be because catabolism is occurring and we're making a lot of acetyl-CoA to go through energy-producing pathways, or it could be that pyruvate is being converted to acetyl-CoA to make fat, okay, because citrate, this product, citrate, is going to be used in biogenesis of lipids, so there will be a lot of reasons for that. If oxoacetate concentrations are going up, that typically is a signal that actually the citric acid cycle is slowing down, strangely. And we'll actually talk about that later, so I don't want to do too much of that right now. Okay. Now, 2 other signals. Let me say this, okay? So that substrate availability is very important, but let me say 2 other signals. NADH can allosterically inhibit this. So a blunted arrow means inhibition. And ADP can activate this. Okay. So it can undergo also allosteric regulation. In fact, this is not a full list of the regulation that it can undergo. But NADH can be inhibited by can inhibit citrate synthase, and ADP can activate it. Okay. These signals, this would be a feedback inhibition signal. NADH is going up, that means it's not being utilized by something in the cell. Typically, oxidative phosphorylation. Okay, if oxidative phosphorylation flux has gone down, NADH concentrations will rise. ADP is, of course, an indication of energy charge dropping in the cell, which means that catabolism needs to be ramped up. And that's citrate synthase regulation. Question, yes?
Is there any inhibition by ATP?
Not that I'm aware of, although I could be just ignorant of that fact. I mean, citrate synthase is pretty complicated. All of these are actually pretty complicated because there are different isoforms. I'm just kind of giving a broad stroke, but it's possible that ATP could inhibit that. I just don't know. Yeah. So, other questions that I can take a shot at in the dark? No? Awesome. Okay, well, let's do the next one then. Isocitrate dehydrogenase. Probably the most important regulatory step in the citric acid cycle is at isocitrate dehydrogenase. Okay, isocitrate dehydrogenase does this: the oxidative decarboxylation of isocitrate to alpha-ketoglutarate makes NADH. Okay, and that's what you're seeing here on the right. It's an oxidative decarboxylation reaction. I'm not sure why this doesn't show this, but there should be a CO2 being broken off here as well. Okay. Right, it makes this alpha-keto acid alpha-ketoglutarate. This enzyme, its regulation is similar to what we just looked at. It can be inhibited by NADH. This, I do know, it can also be inhibited by ATP. So in this case, that is true. Okay. And then it can be activated by ADP. So similar signals. Again, I'm not getting the whole list here, okay, but I'm highlighting some of the similarities in the regulation of these things. Okay. Logic behind the regulation is the same as what we saw with citrate synthase. Okay. Now, if you were to start at glycolysis and work your way down through the regulatory enzymes, you'll find that NADH, ATP, ADP, and AMP all play important roles, okay, throughout, okay, for reasons already discussed. Now, the last thing here, let me go ahead and move on. Let's look at alpha-ketoglutarate dehydrogenase complex. We started the day off with pyruvate dehydrogenase complex, okay, and its regulation. And I said in that regulation, NADH can competitively inhibit it, and acetyl-CoA competitively inhibit it. This complex is virtually identical to that complex, and it also undergoes competitive inhibition by NADH and competitive inhibition by succinyl-CoA. Okay, NADH at E3, and this at E2. Okay. And then the last thing here would be that it can be activated by AMP. And you say, why not ADP? Because. Okay. Okay. AMP is what activates it. Now that reaction, I guess I didn't highlight it over here. It's going to carry out one of these oxidative decarboxylation reactions again, make CO2, okay, and produce NADH. Okay. Fourth step in the pathway. As a total, when you start to consider citric acid cycle regulation, it's not nearly as complicated as, let's say, glycogen metabolism regulation. Okay. And you don't even have to thank me for that. It's just the way it is. Okay. Right. I mean, there are certainly more complications than we're addressing, but they're not terribly important. Okay? Not for what we're going to do in this class. Questions on any of that? Baseball starting tomorrow. Did I mention that? I don't know if I mentioned that. The Rockies are tied for first place right now. I mean, I'm just happy, you know. I mean, we've got as good a chance of winning the World Series as anyone. Okay, so some of you are thinking, that's not what Vegas tells me. Okay, fine. Okay, but they could be good. There's a lot of ifs on that team, but they could be very good, or they could be very mediocre as well. So, anyway, questions on the Rockies? I've got answers. I mean, well, I don't know if I have answers for their problems. I just have answers about, you know. So, we'll find out. If Kyle Freeland is good, if Herman Marquez is good, and if John Gray are good, we're going to be good. That's a lot of ifs. And if our bullpen is good, and if we hit the ball, and catch the ball, and field the ball. There's a lot of ifs. I mean, but, you know, we could be good. So, okay, let me do this. Let me ask you another question, okay? All right. To introduce this. All right, so this is going to introduce our essentially our last topic of the day and one of our last topics of the lecture too. Okay, which of the following would lead to a net synthesis of OAA via citric acid cycle? You have a minute and 43 seconds now to answer this question. A net synthesis, meaning these processes will lead to the accumulation of oxaloacetate. Which of those is true? Okay, so go ahead. Answer that question. I'll give you a minute now and 39 seconds. What do you think? Talk to your neighbor about that. Why is that the case? Is it locked? Oh, there's 7 results. Really? Everyone got locked out? No, people are doing it. Are people okay? You've got actually 74 seconds. And I'll pause it too. Are people responding? Oh, looks like it. Okay, about 30 seconds left. The number of responses is lower than I thought it would be, but keep responding. Okay, about 15 seconds left. Five seconds. Okay. Cutting you off. Here we go. Let's look at these results. Okay, so 33% say that net accumulation of oxaloacetate will occur by the production of citrate from acetyl-CoA and production of alpha-ketoglutarate from glutamate. You know, and then the next most often given response are B and C, that the activation of pyruvate carboxylase and production of alpha-ketoglutarate from glutamate are going to be the most important. Okay. All right, so let's go ahead and look at this, and let me go ahead and try and set the stage as to why this is important, okay? And we'll get to the answer here in a little bit. I'm going to leave it as a cliffhanger for right now, okay? The citric acid cycle is what we would consider an amphibolic pathway, okay? And by amphibolic, that prefix, you have some context for that prefix. You've talked about amphipathic molecules that have a polar and a nonpolar nature. Amphibolic just simply means a pathway that can be both catabolism and anabolism. To start off in lecture 8, I went through essentially how this is a catabolic pathway. At the end of your notes of your group work, you saw that it can produce a lot of ATP. This is a catabolic pathway. Okay. But at the same time, it is also an anabolic pathway. Okay, and so let me do this. I'll come back to these cataprotic and anaprotic reaction definitions here in a little bit, but let me go here and pull this up, and let me just give you some sense of this, okay? In terms of anabolism, okay? And this is why we consider the citric acid cycle essentially the hub of metabolism. If you start looking at genetic diseases, you find very, very few genetic diseases that have mutations in these enzymes. And the reason is because they typically lead to the death of the organism before birth, okay? So you just don't see them, right? And the reason is because of how important it is in both catabolism and anabolism, okay? And so let me do this. Let's look at this, okay? The molecule citrate, okay, as we will talk about later on, can be used in the biogenesis of lipids, okay? Now I drew that little line there to represent that citrate will be exported out of the mitochondria into the cytosol where lipid biogenesis occurs. Okay, that reaction, okay, is a very important process, of course, in the cell. Okay? In addition, alpha-ketoglutarate, okay, is a single step away from becoming glutamate. In fact, we saw that in our malate aspartate shuttle. Right? Glutamate is a single step, no, that's not what I wanted to do. Glutamate is a single step away from becoming glutamine or other amino acids. Okay, so many of the amino acids, okay, that we can get, that we can make ourselves are going to be derived from alpha-ketoglutarate. Okay, glutamine can be used in nucleotide synthesis. Okay, and this is a source of glutamine. Succinate, coming down here, is the starting point of some fairly complicated pathways that make heme groups. Heme groups that would be found in myoglobin, heme groups that would be found in hemoglobin, or heme groups that are found in cytochromes, which are very important proteins found in the electron transport chain. Okay? Those are biosynthetic pathways. We've seen this, we've talked a little bit about this in the malate aspartate shuttle, but malate can leave the mitochondria and it can become pyruvate through several steps that we've already talked about in this class. And pyruvate can be converted to glucose or several amino acids. Okay? And then of course glucose can be used in the production of glycogen, or it can be used in pathways that we need to talk about that are glycosylating proteins. Okay. And then finally here, and this is not a comprehensive list, but it's a pretty good one, oxaloacetate can become aspartate. Okay. So every single one of these steps that I'm arrows pointing away from the path, these are all the starting points for biogenesis. Now, if conditions in the cell are leading to increased flux through biogenesis, that will start to decrease the pools, the substrate concentration pools of the citric acid cycle. And flux through the citric acid cycle can start to be drawn down because you're pulling intermediates away from it. Okay? And so these reactions are sometimes what we refer to as cataprotic reactions. Okay? And these pull intermediates away from a pathway. In this case, the citric acid cycle. And that can then lead to an overall reduction in flux. Okay? That can be dangerous, harmful. Okay? And so to maintain homeostasis in a steady state, you have to have what are called anaprotic reactions. And anaprotic reactions are those that build, if you will, or put back intermediates. Into a pathway. Okay? And one of the intermediates, for instance, in the citric acid cycle, for instance, is replacing oxaloacetate. Very important. Okay, because if you're going to replace oxaloacetate, you can have a net increase in oxaloacetate concentrations, then you can maintain flux, okay, through the citric acid cycle, which of course is needed to continue to go on through for biogenesis as well as, of course, catabolism. Okay? Now, I'm going to go ahead and give you the answer, and then we'll come back and look at why that is the case. Okay? So the answer is B and C. Okay? These two, production of alpha-ketoglutarate from glutamate and the activation of pyruvate carboxylase, will lead to what are called anaprotic processes. The top one is not. We'll look at why that's the case on Friday. Okay, so I'll fill that in. But that's the answer, B and C, okay? All right, have a good rest of your day. Enjoy the nice weather. It's supposed to rain tomorrow. Oh, we're good on the quiz. Yes, you're good on the quiz. Thank you for asking.